Thank you. And thank you. It's really good to be here. And enjoying being back in Pittsburgh. I came in over the weekend and being able to go around my old stomping grounds. So also now good to be back on the university campus. So as a heads up from the someone on my last talk said that my title looked like I was hitting one of each people's phobias. So there are a couple spider pictures at the end of the talk as a heads up. My background, I came here, I was an undergrad at MIT in mechanical engineering, working on on mechanism design and precision design. I spent my graduate years here with a side detour off to Japan for a summer on an NSF-EPSI program, after which I came back and took on a faculty position at Oregon State University, where I was hired as part of a push to build up a robotics program at Oregon State University. And when we got there, we basically got a big empty room and some space and said, okay, build a robotics program. And so we renovated this big empty space. We looked a lot at like the history of the RI, pulled some inspiration from there, put together a big multi-robot group, large lab with adjoining student desks and faculty offices. We've got, in the time I've been there, we've grown from a few faculty members to 10 core faculty, plus a number from other departments, with centers in physical interactions and robust autonomy. My background, while I was here, I worked heavily in snake robots, and so this slide is not going to be new for most of the people here, but looking at how we can make chains of actuators move through the world and across different environments. And so that was a lot of the work I did while I was in Howie's group was centered around that problem. We then expanded to other locomotion problems, looking at sidewinding on sand, and continued some of that work at Oregon State University, looking at various ways of building soft snakes. And so this was a project with Yeatman Gooch, who was a faculty member with us, also got his PhD here, is now with Facebook, working on Oculus haptics. And then Kelly Brennan, who recently got her PhD, and did some other work, some snake-adjacent work. I was on a paper with Michael Porter, who's amazing bioinspiration researcher now at Clemson. We're looking at the structure of seahorse tails. And so he'd been doing a lot of work on the mechanics of why they're square, and we couldn't figure out why they tend to be tilted at an angle. And so we spent some time looking at it and realized that the reason seahorse tail looks like it's tilted at an angle is because you've stretched it out. The neutral position for the tail is actually that curled up position. And so if you look at it in terms of what's your best even range of motion around the true neutral position and not the lab neutral position, you end up getting a tilted mechanism. Some of the snake robot work that I've continued to do more recently is built off of Sidewinders. And so we're looking at, in this case, how to build a pneumatic Sidewinder. And so that's a triple helix mechanism because you've got the McKibben actuators have helical braids in them. And then we arrange the McKibben actuators into a helical shape. For the neutral shape of the robot has the McKibben actuators helical, which we enforce by having them pass obliquely through the separation discs. This design is built off of some work Gina Olson, who's here now, did while she was at Oregon State, of doing these bundled McKibben actuators. My student Farhan and I went through and figured out how to angle those actuators such that they form the mesohelix, and then when we contract one of those actuators, it forms a macrohelix that then is the sidewinding shape, and by phase shifting our way through the different through which actuator we contract, we're able to shift the macrohelix along the body, and that's the helical tread motion that we need in order to get sidewinding. I've also done some other work on looking at how actuator placement, and this fits into my theme of how actuator placement is important in understanding robot capabilities. Another example of that was some work with Jonathan Hurst, also an RI alum, and our co-advised student Andy Abate, where we're looking at the walking robots that are Jonathan Hurst's specialty, and his. And they'd found when they were designing Atreus, which was the second generation of their lightweight agile walking robots, that they were concerned that if you have a hip knee motor, that you're passing all of the forces for the support through both actuators, and so that they felt that that might be extra load on the knee. And so they had the idea of make it a double hip with passive knees linkage in order to avoid any serial pass through the motors and have the motors in parallel and share the load. But then when they set that up, they found out that actually it gave much worse energy efficiency than the previous serial design. And we did, when they went back to serial design like this for the third generation Cassie robot, that they found a much improved efficiency. And so the question was, what's happening there? Why does it happen? And what we found out, and then we're able to mathematicize in terms of power, we call it power quality, is that if you've got those motors in parallel, when you're in stance, just holding stance, they share the load nicely. But when you're swinging while in stance, one of the motors is backdriving the other. And so from that, we were able to show that if you can stay out of the, if you have your, the power in the motors, if one, you can look at it as if the power in the motors, one's positive, one's negative, that ends up being a bad power quality. And so you can evaluate for a mechanism for a given gate motion, what is the, is that mechanism actuator placement well tuned to the task? And so it turns out to be task-based, where you can say that you had bad power quality when you're in that positive, negative, second or fourth quadrant, but good power quality if you can stay out of it or at least stay on the edge of it. And so we're able to build up a strong theory about what makes a good mechanism-task pairing. And one of the things that comes out of it is that where a lot of metrics for tasks come out to be something like a 2 norm, which is rotationally invariant. That's changed as you change mode shapes, as you change your task, your power quality doesn't change. The power quality is a lot more like an L1 or an L infinity norm in that as you change your grid, if you were to take a Manhattan grid and rotate it, the relative distance between points changes as you rotate the Manhattan grid. And a similar thing happens here for task tuning to actuator placement in a robot. Some other work that I've done recently, as part of an overview, is I'm on an EFRI team. So this is a big NSF 4-year grant where across the 2 rounds that they awarded it, there's about 20 teams working on novel soft robot concepts. And so our concept is based on using buckling structures and actually taking advantage of buckling. And so this is a robot that Nick Ravish, who's leading the team, and his student, and then one of my students and I have been working on, where we can build a hinged oar out of a tape measure and control the angle of the tip of the tape measure and the base length of that triangle. And then by pumping that angle and that base length, we can actually get swimming motion. And so the technique is and then to understand what's the best pumping motion, we'll use some of the geometric mechanics techniques that I'll be talking about later in my talk. And more recently, in my time at Oregon State, I've also started the second sideline of work looking at spider-inspired problems. And so we've got a number of things that's revolving around sensing. And so at the end of my talk today, I'll be talking about some of the spider-inspired sensing work that we do and how that's merging some of the engineering and biology with some applications. And as the last piece before I dive into some of the more technical ideas of the talk, I'd like to speak a little bit about some educational work that I'm doing within the robotics program at Oregon State. And so one of the things that as a feature of our program is that we're bringing in people from many different disciplines. We've got people coming from the traditional core engineering disciplines, mechanical engineering, electrical engineering, computer science coming in. We also have people coming in with backgrounds that are outside of that area, psychology, people with strong dance backgrounds for some of the human-robot interaction work that we're doing. And so when they're coming into the program, we need a way of bringing everyone up to speed and getting a good normalized, I call it a robot boot camp, of bringing in those baseline technical skills of working with a robot that make graduate students so much more effective at being able to take their work and apply their work and and just understand what happens below the robot algorithms and understand that robot stack. And so I've been working as part of our introductory class. It's the second class they get in the sequence. First class is high-level robot algorithm ideas. Second class is this full-stack robotics class, where we take a number of small robot kits. So they don't have all the they don't have all the fancy features that you get in a high-end robot, but they expose the students to all of the other engineering problems that get solved by the time you buy a high-end commercial robot platform. And so through this course, we expose them to the fundamental, just working with an arm in a car, so that even if they're going off and working on higher level algorithms, they've had all that exposure to what does it mean to move as a car or move as an arm. Working on system setup. So we make sure that everyone's turned a screwdriver, understood what happens when you can over torque screws, strip screws. They've had the chance to be exposed to that. One-time assembly with plastic rivets. Students who haven't had that background learn that, you need to be careful and assemble things, and you can't always back out. Electrical setup. If you plug the wires in wrong, the magic smoke comes out. Better to do that on a $80 robot here than on someone's tens of thousands of dollar robot in the field. And then also the computer setup. So robots come with very often, even these cheap robots with a Raspberry Pi, you've got a full Linux computer on board. And so a lot of students come in, don't have full exposure to the ideas of computer security, how to set up a computer, how to configure the computer. And so I've got a set of tasks set up to pull them through doing the full secure setup up to network security, and then setting up version control, so setting secure pipelines from their computer, GitHub, and the robots. They can pass the code around and really make sure that everyone in the program can rely on everyone else in the program to have at least seen these basic ideas, even if they're coming in from outside fields. And then bring in ideas of like what are good workflow patterns to use. So ideas of offline testing, take your robot code, copy a version onto your computer, mask out the calls that actually go to motors, so replace those with null calls, so that you can test all the business logic of your code before you actually run it on the robot. Sensor calibration. Students, depending on their background, come in not knowing that how to do any of the data processing on even like a simple 3-channel grayscale sensor for lines. Students get surprised when, the blue carpenter tape I gave them isn't actually contrasty in grayscale against the brown floor that they put it on, even though it looks like high contrast to their eyes. All these things that are going to be good baseline principles to build on as they move forward in the graduate program. And then finally, when we start looking at things like publish-subscribe models, robot operating system causes me no end of problems at conferences because I have to filter out is the people talking about me or the operating system. But if you want to teach publish and subscribe, it's very unwieldy. There's a lot of overhead to learning it. And so that's why I put together for this course, and it's available at rossross.org, is it's a lightweight publish and subscribe framework for quick prototyping and educational purposes. The core file is about 300 line Python file, about half of which is just comments and documentation. So it's fairly small. It's a minimal interface to Python multitasking. So it gives them safe threading for preemptive multitasking, or an alternative version that uses cooperative multitasking. So you can see just the bare bones minimums of how these concepts work. We can talk about the promise and peril of using threading and show race conditions. There's good ways of showing this. And the core components of it are a message bus with some rewrite protection in the threaded version, and then a consumer producer wrapper class that allows you to take any function, say read from motor, or take in some sensor values and decide where the line is. You can write those functions individually, and then wrap them in this consumer producer class, which will run them on a timer with in their own threads if you're doing the preemptive multitasking, and just get that bare minimum idea of how to do a publish and subscribe setup. And you can use that as for educational use by providing that basic framework as an assignment. I can give them the spec and in a week have them go through and put together the basic pieces. And then I can also provide them then with the following week with the reference code and have them port over into the reference version. And that then gives them that spiral learning piece of having tried it once themselves and then very quickly see a reference implementation without and be able to learn quickly from that. Where again, the idea is these are graduate students who are trying to quickly do a quick wedge through all of the robot concepts that we can that we can get at, so that they know what to look for and what to learn down the line. And at that point there, I'm going to switch over from that overview piece and talk a little bit about the core technical work that we do in my lab and the paradigm that we use for thinking about locomotion, along with some tools for taking these core concepts and big ideas and actually making them concrete in example systems that tie in nicely to some basic locomotion principles. And this core idea is looking at the geometry of locomotion. And so the core idea there is that many locomotion problems are area perimeter problems in which the net displacement relates to an area swept out in the robot configuration space. And such that, for instance, if I take a system here, it's a 3-link swimmer, I can look at its physics, and I can write down a function so that the distance it travels over a gate cycle is going to be based on how much signed area I enclose with the gate cycle. And then, for example, sweeping out this path there that encompasses all of the negative region and none of the positive region is going to be like the longest stride the system can take. It's going to be the furthest it can go in any simple cycle with one cycle. And then the second part of this principle is that the cost of motion is perimeter-based. And so what that means is that if I look at the configuration space of all the different shapes it could go into, then I look at a sequence of gate cycles of different sizes, that I'm going to expect a correlation, and sometimes a linear correlation, but at least a correlation between the perimeter length of that cycle and the time taken, or otherwise, or energy needed in order to execute that cycle. And so when we put these principles together, we end up with an idea that a gate cycle that is shorter, that doesn't completely enclose a negative region, but is able to be completed in a shorter time, is going to be a better gate than one that completely exhaustively covers that sign definite region. And so in this case, it's we'll talk more about these details. That's 3/4 of the time to execute. You can clearly see because I matched the appropriate inputs there, and it got 85% of the net displacement because the outer edges that it gave up were very low yield compared to the inner rich region. And then we've got some extensions that, and that material, that was when I was here, I had that framework pretty much worked out. And so since I've been here, since I've been in Oregon State, I've been working on various extensions. And so one of the extensions that we've been looking at is systems with shape spaces of 3 or more dimensions. So we can use that same principle there that I just drew for the simple 2-joint system for this 3-joint parallel linkages system here. And so we use those same principles there to find that optimized gate for how this system, this shape could move. And then also looking at data-driven geometric locomotion, which is the idea that we could, rather than going through an analytical model to find those area functions, we can get the relevant information off of online data recorded online as the system moves, and then use that, put together what eventually becomes a geometrically informed reinforcement learning algorithm. So moving forward from there, those are the big ideas of this area-based paradigm. And to put some examples of how we make that work, we start with a constraint-based locomotion model. And so to explore that, we're going to take our simple 3-link system. This is a minimal locomoting model where I have a position and orientation for the middle link, and then a shape that is the 2 joint angles. And when we take that system, for many physics models, we can represent the physics model for the locomotion of the system as a constraint where there's a constraint matrix that relates allowable combinations of the body and shape velocities. So the body velocity is the forward, lateral, and rotational velocity, and the shape velocity is the rate at which the joint angles are moving. And for many different physics, the allowable combinations of those velocities that respect the physics constraints are in the null space of this constraint matrix. And as an example of what that means, let's look at skaters. So a skater system has wheels or skates on it that prevent the wheels those wheel sets from moving laterally. So they're completely prohibited from moving laterally, but are allowed to translate longitudinally and to rotate freely around the respective centers. And so we can go through and we can write down the Jacobians from the body velocity and shape velocity to the body velocities of each of those wheels. And then we can say that the y component, the lateral component of those velocities, has to be 0. So I can extract out the y component of those Jacobians, take those 3 rows as their own constraint matrix, and say that any allowable combination of body and shape velocities under these physics has to be in the null space of that set of lateral components of the Jacobian. For free fall and inertial systems, if I'm like on an air hockey table floating in space or in a inertia-dominated fluid where I don't need to worry about the viscosity, then the momentum or momentum-like term for the system, if I start at rest, has to stay 0 for all time. And so I can write down that momentum function for the body and shape velocity. I can say what's the overall linear and angular momentum of the system. If there's a fluid around it, I can do added mass for the fluid and map that all through and say that the only allowable combinations I can have of those variables if I start at rest is to stay at inertial rest, keep 0 net momentum. And then finally, if I'm looking at systems in viscous fluid, I can look at the overall drag that acts on the body. And if you're in a viscous fluid, the net reaction drag is going to balance out. Your inertia is small compared to your viscous forces. You're very quickly going to quasi-static equilibrium, and any force I apply over here is countered by a force over here. If I have more drag force for moving sideways than longitudinally, so I can push off and then go forward, and I can anchor and pull, and so I'd still be able to move even though at any time my total drag force on the body is 0. And so I can use that drag force mapping as my constraint. So once we have a constraint model for locomotion, that tells us I can test any combination of body and shape velocities and say, does this respect the constraint or not? But that's not really what we want for locomotion analysis. Instead, what we want to do is we want to specify the shape velocity and say, given that shape velocity, what is the null space complement of that in those constraints? That is, what body velocity is compatible with the physics and that shape velocity. And to do that, there's a technique for constraint solving that I like as a general technique, and I've not seen it taught everywhere, so I like to go over how to work with it, which is that you separate your constraints into the portion that acts on the known and unknown portions of your velocity when you're solving for a null space complement. And then because the other side is 0, you can pull over all of the unknowns to one side and the known pieces on the other side. And then you can invert that constraint on the unknown components, multiply it into the constraint on the known components, multiply those matrices together, and then you end up with this matrix called the local connection, which acts like a Jacobian from your shape velocity to your body velocity. And so this acts conceptually like your manipulator Jacobian, and that you take your joint angle velocities and then you tell how the end effector is moving. But in this case, the end effector is the body itself. And then to geometrically understand what that means, we can think about the matrix there as a stack of row vectors, each of which interacts with the shape velocity via dot product operation to produce one component of the body velocity. So we can split that out, and we can then say that each of those vectors is a function of the joint angles, and so becomes a vector field over that space, really a covector field if we're being formal about the differential geometry. And then we can go through and we can say that as we execute a gate, we can see that the system is going to move forward laterally or rotationally whenever its path through the shape space is in the direction of the corresponding field. and is going to have no motion whenever its path is across the field, or it's going to go backwards in that direction when it's going against the field. And at that point there, we can start to think about, well, how could we place cycles in order to get more flow along the field more than flows against the field, or to flow along a field as much as flows against the field if we don't want any net motion in a direction. But if we start trying to reason at that level, it very quickly becomes subjective and intuitive and doesn't really give us anything we can work with programmatically. So instead, to understand those ideas of flow more along the field and against the field, we can turn to two principles about these fields that say how that works. And the first of these is non-conservativity. So with non-conservativity, the minimal example for that is a wheel that can change size. So if I take that wheel and I roll it clockwise by a half turn, it moves forward. And then when if I shrink it to half diameter, it doesn't move, but then when I roll it counterclockwise by half a turn, it moves back less than it had moved forward previously. And then I return it to its original size, and it's now moved forward in the original. It's now in the original orientation, but has moved forward compared to its original configuration. And if we look at that motion from the perspective of these connection vector fields, what we're seeing there is that the initial roll was moving along the field when it was big, and then changing shape moved it across the field to where the field is small. The second roll was moving backwards against the field when the field was small, and then returning to its original size is moving across the field again. Such that that net forward motion corresponds to how much we gained by moving along the field when it was big, minus how much we lost by moving against the field when it was small. And so if we look then, say, how do we actually characterize that that difference in terms of the field properties and gate properties? There are three factors that come into play. The first is how steeply does the vector field change across the space? So the steeper the derivative of that crosswise vector field, the more difference we're going to have between the forward and backward motion. The second factor is the span in the space that we cover. So the more of that, the more we change the radius, the more we're going to interact with with that change in the field. And then finally, the roll-wise span. The bigger a rolling motion we do, so if we roll through a bigger angle, we're going to end up with a bigger difference at the end. And so if we put those together, we then end up being able to say the net displacement is equal to the area. So multiply the two spans together, we get the area of that loop and that in the space, multiplied by the derivative of the vector field, the crosswise derivative of the vector field. And so that gives us our net displacement forward minus backward. And if we take that principle and then we extend it and do some more calculus to look at more complicated fields, and maybe with gate cycles that aren't just boxes, what we end up with is, coming back to Green's theorem, which is aspect of Stokes' theorem, which says that the derivative we looked at of how steeply it changed crosswise, that's measured by the curl of the vector field, which accounts for doing crosswise differences in two different directions, and do they amplify each other or cancel each other out. So that derivative we looked at was a special case of the curl for a vector field that points in one direction and changes in one direction. The area multiplication there then becomes an area integral. So we're looking at that curl individually at the different pieces to integrate back up the changes in the field from one side of the gate to the other side of the gate. And then this is our first principle for what do we look for in the field? We look at the curl of that field. The second piece we look at then is non-commutativity, which we can see from looking at a differential drive car, where if we drive forward, turn, drive backward, and turn the other way, up to a small angle approximation, we've achieved a net lateral motion, even though the car never moved laterally on its own. It was only the combination of the turning and forward-backward motion that gave us a net lateral motion. And that net lateral motion is proportional, as I said, in the small angle limit, to the size of that forward-backward motion multiplied by the size of that angle that we took, that we turned through. And if we look at that from the vector field approach, what we're saying is that the forward motion was moving the wheels together. So the two shape variables are wheel 1, wheel 2. So if we move the wheels together, we end up moving forward. The turning was rotating to move the moving the wheels against each other, so along the theta field, back along the forward field, back along the theta field. And then that amount that we moved forward by corresponded to the span of the gate in that wheels together direction. The amount we turned by corresponded to the span of the gate in the wheels against each other direction. And that, so that once again we get an area-like term. But now that area term, instead of being a curl term, is the Lie bracket term, which you can think of as an operator that measures how much the rotation of the body frame changed the direction in which the car's forward direction was pointing in the world. So as we rotate by theta, that turns the body forward x starts pointing in the northeast direction instead of the pure north direction. And so that Lie bracket operator there then tells us is a way of measuring that coupling between rotation and change in forward direction. And so pulling these ideas together, we get what's called the curvature displacement formula, which says that the net displacement, and I've got footnotes here for people who want to play the deeper math game. I won't read them out, but we've got the net displacement is equal to an area integral of the curl, or formally the shear derivative, which gives us that forward minus backward motion. So as if I'm swimming around, sometimes I'm reaching further. I've got more leverage on the world. I've got a bigger wheel, and then as I tuck back in, I've got a smaller wheel. This local Lie bracket, this parallel parking term, which says that I might nudge my body one way or the other as I move my limbs, and so we need to account for some parallel parking effects. And then some higher order terms that correspond to the things we threw out when we looked at the small angle approximation with the parallel parking. My thesis work focused on how, by making a principled choice of coordinates, which I'll touch on briefly, we can often get rid of those higher order terms, at which point we then get this dA operator. It's the curvature of the constraints, talking about how changes in one constraint, moving in one shape direction changes the constraints on the system, and in a way that we can exploit to get that cyclic motion. And we can make this as an operator on those connection vector fields. And so that then gives us the idea that we can take these vector fields we computed for the swimmer, and we can turn them into this curl plus Lie bracket term as functions over the shape space. And we can execute a gate cycle, and we can see that this gate cycle encompasses a sign-definite negative region in a clockwise, so right-hand rule negative direction loop, and so is going to move the system forward, but has net zero encirclement in the y and theta fields directions, and so it's not moving the system anywhere laterally or rotationally. Once we had this principle, then we can also go through and then start looking at things like, we can make some very strong statements about how displacement changes as we scale up a gate. So what happens if you start making a bigger or smaller motion? So for example, if we have a set of circular gates that increase in radius, those are in a roughly constant region of the dA field, increasing quadratically in area. So we have a somewhat quadratic-like growth in the net displacement per cycle. So you get superlinear growth in your net displacement per cycle as you increase that gate radius, because you're better taking advantage of the nonlinearities, the higher order terms in the system dynamics. As we go to bigger circles, however, we start encompassing some of the opposite sign region of the space. And so what that does then is that means we see diminishing returns, then actually a loss of performance in the gate as we go bigger and bigger, because we're now doing motions that actually go beyond what's useful and actually start pushing us backward the other direction. We can also look at things like maximal strokes. So if I want to say what's the biggest lunging step I can take, that's going to be this gate that traces out the zero contour, separating out the positive and negative regions of the space, because that's going to and that's going to beat any of the circles, because any of the circles either had to give up some negative region or accept some positive region. And so that zero contour gate is going to go further than any of those circle gates would. And as you may have noticed when I switched back from the excursion into non-commutativity, non-conservativity, into showing how we actually use it, I switched over from using the middle link of the system to using this floating reference frame with an average orientation and center of mass-like term. And that comes into a change of our body frame definition, where we were able to get rid of the higher order terms in that constraint curvature equation by shifting from that middle link to weighted center of mass and weighted mean orientation of the lengths. And the basic principle there is that when you look at the motion of that average frame there, you can see this average frame is basically moving monotonically along forward from the initial configuration to the end configuration of the gate without rotating very much. Whereas if I tracked the center link on the same trajectory, I would have seen something more like this, much more loopy. And the principle is that as you move forward at an angle, you pick up error that shows up in that series expansion. The higher order term errors correspond to large forward motions well at an angle. So if we can choose a body frame that doesn't ever have a large excursion in angle, then forward motion always counted as forward motion. So that parallel parking term gets small, and the higher order terms get really, really small. And so we can actually do a principled optimization in order to find those best coordinates. And the basic form is if we take the original middle link frame expression for the theta field, so this is how the system is going to rotate as we change shape, we can perform a decomposition on that field to get a curl-free component and a divergence-free component. This is called a Hodge-Helmholtz decomposition. And if we perform that decomposition, the curl-free component here represents the gradient of a change of coordinates that we can use to cancel out the body frame rotation. So we can make a body frame that counter-rotates the center link as much as is possible while still respecting the physics of the system, while still respecting that if I perform a gate cycle that gets me a net rotation, I still have to have that net rotation. And so we can use this to decomposition in order to find how to make our get the system coordinates that give us the best lens on the system motion. And as a side effect, the remainder, when we do that decomposition, becomes the new A theta field. So that's what the vector field looks like for the rotation of the body frame in the new coordinates. So coming back to our outline, so that covers the yeah.
Should the negative grad data, should that also be a minus sign?
So the negative of the so what we do there is we want to find the grad beta should be the negative. Grad beta should be as close as possible to the negative of the original field. So when we add them together, they cancel out.
Right. So then beta is the rigid body transformation.
Beta is the transform from the center link coordinates to where that floating frame exists. And so we want the gradient of beta to be as close as possible to the negative of the original field, such that when I say how is the center link moving, and then how is the new frame moving relative to the center link, those should cancel out each other as much as possible so that the new frame only shows the true motion of the system and not any extra motion. So in the same way that like if I was doing a motion tracking on you, you wouldn't want to like track where I'm walking in the room by how I'm moving my fingertips right now, because there's lots of extraneous motion there. You'd rather track how my torso is moving, or if I'm bobbing my torso back and forth, you'd rather track something like my center of mass. And so this tells us how to get the motion of the center of get a center point that has as little extraneous motion as possible, remove all the motion that's going to be canceled out over a cycle, and leave only the true motion of the system. If you do this with a inertial freefall motion, you in fact get the center of mass when you do this on the position component. So moving back to our outline, we have this idea that we've talked about how the net displacement is area-based. Next piece of this outline is talking about the idea that the cost of motion is perimeter-based. And so the basic core concept here is that the range of motion that you get for a gate cycle corresponds to the product of deformation speed. So how fast are you changing your joint angles, multiplied by the time that you take. So a gate with a large range of motion in the shape space has to either involve fast joint motions or take a lot of time. And as a basic rule, the deformation speed corresponds to the instantaneous effort that you're putting in. So the faster you're changing your joint angles, the more effort you need to put in. And you're barring other effects we can take into account. The first order effect is that instantaneous effort correlates with time, such that if we take a system with our shape space dynamics and we fix the instantaneous effort as a fair comparison across gates. So I want to say I've got this much effort that I can use to move. And we're going to fix that across any gate that we put in. If we look at the time taken to execute a set of gates with increasingly large range of motion, that time taken is going to correlate to the perimeter of that gate. So there are nuances there. For instance, we can put weighting on the shape distances. And so if we look at a system that is moving in the CU shape, so it's moving evenly, that's going to take a lot more effort than moving in this SZ shape. The top one ends up dragging if you're in fluid, you end up dragging sideways through the fluid a lot more than when you're doing the Z-shape motion. So you can put in a cost weighting term that actually says that the distance along the even axis is longer than the distance along the odd axis, and so we can use that when we're talking about what we mean by perimeter. We can use this extra distance weighting. And then there's also other effects, like for instance, motion when you're in a fairly curled up space tends to be easier than motion when you're closer to straight, just because of the leverage that you've got on the body and the way pieces get moved. And so that ends up meaning that the overall shape that we're looking at for the configuration space is not just stretched, but is actually also curved. And so any path length perimeter effects that you're looking for on the space, you actually should take into account that curvature when you're looking at what the cost is. And that means things, for instance, that if you look at the set of gates that have that increasing radius, the time per radius line is not in the shape coordinates is not going to go linear, but is actually going to end up sublinear, because when you're in a dome, your perimeter length grows more slowly as you move away from the center. So we can take these into account, but this still gives us the principle that the cost of motion is perimeter based. And then moving forward, we get the idea that this now gives us tools to go back to the idea that locomotion is an area perimeter problem, where we said that we're looking at for a way of balancing how long does it take to complete the gate cycles versus how far do we go in the gate cycle. We don't want to take a very long lunge, because that long lunge there is going to takes me a very long time to make that cycle step, and there's a diminishing returns at some point after my easy stride. And so when I'm walking, there's of course extra effects in there, but it's the same principle that I want to balance time taken against distance traveled. And this turns out actually into a really nice fundamental geometric principle here, where because we start off with this idea that net displacement we said was an area integral. And that means that the gradient of the net displacement is the gradient of that area integral. And so then we can go through and we can bring in that this idea of the Leibniz rule, that when we take the gradient of the integral is the gradient of the boundary times the integrand, which ends up then giving us this idea that we can insert the gradient into that integral process. And there's a bunch of fairly hairy math here, and I'll come through to where it comes into a cleaner expression. And then for this 2D case here, it ends up saying that we can take over any variation we might make in the gate, so any change in that path, we can say how does that, changing the gate, the input parameter to the gate, how does that move each point of the gate outward? Multiply that by the value of the constraint curvature at that point, and that tells us in the parameter space what the benefit gradient of moving that, of changing that gate parameter looks like. And overall, that turns into basically an outward pressure from the constraint curvature. So the constraint curvature is saying, okay, you want to expand your gate cycle to go as far as possible. You want to keep expanding outward to go further per cycle. When we then take the efficiency as the ratio of net displacement to perimeter length, we then end up being able to say that the gradient of that ratio is proportional to the gradient of the displacement minus a weighted gradient of the perimeter length. And so we pull that in, and that acts as a surface tension from the distance metric, saying that long gates are expensive. And so that's a surface tension, like a soap bubble, balancing the pressure to inflate a soap bubble with the surface tension to make it smaller. And if we can actually then directly put that into an optimizer, and starting from that zero contour, we can shrink down and apply and solve until we hit the equilibrium between that surface tension and that pressure. And that gives us this gate here that I showed earlier, which is takes only 3/4 of the time to complete as the zero contour gate would, but gets 85% of that net displacement because it's only giving up the very low yield regions. And so it's expanded basically until the until that expansion becomes not worth it to expand any further.
Alpha 2, or are they Fourier coefficients?
You can do it however you want. We have a software tool. I've got a software tool that I think we work with Fourier coefficients, but it can be any parameter set you want. It can be wavelets. I've done a project where we have like a couple of Fourier parameters and then bump functions on top of the Fourier parameters. It's when you go through and you do the gradient, and be happy to talk about this more. The formulation works really nicely. For variational calculus, sounds really scary, but once you actually start doing the details of how it works really nicely for any parameters you put in, and you can change between one set of parameters and another with just a Jacobian matrix that you stack onto one end of the derivative. Welcome. So at this point now, we've covered locomotion as an area perimeter problem. And then a couple of questions I often get. One is, how does this work with 3 or more dimensions? I've used perimeter and area, and what does that mean for higher dimensions? And the basic idea is that when we're looking at that perimeter area problem, really this is what we're looking at is we're looking at a 2D version of a 3D problem that has flux coming into and out of the surface. And that scalar value that I've plotted up in the top plot is really a measure of magnitude and sign for this out-of-plane flux property. And we're looking, when we do the area integral, we're actually looking at how much flux from this field is going through the loop. And so when we go to three dimensions of the shape space, the flux field becomes a 3-dimensional flux field. And you can think of this expand and contract to maximize area perimeter pieces as expand, contract, and rotate to orient, rotate and curve to orient. So so you can imagine almost like a sail problem. Like you've got this vortex-filled wind map, and you're trying to build a wire loop that is as short as possible, but catches as much flux going through it as possible. And so all of these growth, all the rules for how do you grow the field, those work out really nicely into a grow and bend. And so in 3 dimensions, and then you stop using the word curl, but the math in differential geometry takes us up to arbitrarily high dimensions using terms like exterior derivative. And you always get, here's a loop, and then the constraint curvature tells you this is how you could deform the loop in order to increase the flux that's going through it. And so you can, once again, go through and start varying your gate parameters until you hit an equilibrium point where it's no longer worth it to expand or twist your gate loop any further. And we have all of this material built up into a MATLAB package on GitHub that you can grab this. It's got a bunch of stock systems already built in. You can play around with them. It's got a kinematics toolbox for gluing together your own higher dimension systems and building all these plots and animations, and also running the optimizer. And so that's the 3 dimensions. The final technical piece I'd like to talk about now is data-driven geometric locomotion. And so the idea here is, what if the system does not have a nice analytical model? So the examples I showed at the beginning, I said, OK, we can write down the physics. The first principles physics treatments gives us this really nice structure for doing this analysis. But the same principle also holds in general for any kind of action-reaction motion, that your first-order model of an action-reaction motion is going to have this structure. And so we can use those ideas in order to build out our intuition for how the system should move. And one way to do that is to go through, and this is work done here at Carnegie Mellon, of go through and twitch the robot in its environment. This is one of Howie's snake robots in the bead pit, and and we're twitching it, and we're looking to say, how does the system move as we twitch it in different shape modes? But that's fairly prone to error. There's a lot of transients as you're starting it, moving it. It's time consuming. So it's not what we'd like to be able to do. Instead, we'd like to be able to do something like take this video here and look at that motion there and back out the principles of locomotion for this system in this environment directly off of the observed motion as it moves through longer range trajectories without the start-stop transients. And so this is then some work that Shai Revzin at Michigan and his student Brian Bittner and I put together for building what's essentially a geometrically informed reinforcement learning approach to understanding this kind of locomotion. And so the basic principle here is I've got a 3-link system here, and we're going to give it a gate cycle, but we're between running the gate cycle and the actual shape it moves through, we're going to add some noise to it. We're going to put it in the viscous environment, but then I'm going to throw away anything I know about what the environment is on the simulation end. I'm going to do, none of my analysis is going to use anything I know about the input cycle or the environment. And we're going to have it execute this noisy cycle gate. And then as it executes that noisy cycle gate, we're going to record its shape trajectory over here on the left and its position trajectory. And then we're going to go through and we're going to say, well, first, what gate did it actually execute? Because we've thrown away any knowledge about that. And so the basic principle here is we're going to start by unpeeling the the trajectory cycle from the shape space. We're going to look at those individually in the coordinates we choose to measure it in 2 joint angles. Then we're going to use some of Shai's math to fold that back to a single multi-valued cycle rather than one long wave. And then we're going to do a Fourier fit in that space, which is more stable than trying to fit to the whole long wave. It better matches the moments that different points have on the fit. And then we're going to put that cycle back into the shape space. And so now that gives us a nominal cycle, the nominal gate cycle the system was moving with. We can then take any point along that cycle, and we can zoom in and we can look at all of the data points from all of the different cycles that were geometrically close to that point in the cycle. And so this is one of the key features here is that we're geometrically associating data from different time cycle points at different times in the extended cycle. And each of those data points has a shape velocity and a position velocity associated with it. And so when we have those there, we can then take that all those data points and we can say, what's the plane that best fits all of those vectors in that neighborhood? If I collected all those vectors at the center of that neighborhood, what's the plane that best fits that shape position velocity combination? And that's our local gradient of position with respect to shape, which is that A matrix that we put together previously from first principles. And looking at that in parallel and perpendicular components, if we take the difference between the product of those 2 pieces in different orders, that's the Lie bracket operator that we previously solved for. Then if we take that plane and those planes and do that fit at several different points in that neighborhood rather than just at the center, we can ask how that fit changes across that neighborhood. That gives us the derivative of the A matrix, which if we look in parallel and perpendicular components and take the off-diagonal terms, the difference between those is the curl. It says how much we're not locked in one place, and so if we do a cycle, we're going to get more forward than backward motion. So we put that curl and Lie bracket piece together. That then gives us, with that gradient math I showed previously, gives us a direction along, and do the same thing for the cost of motion. That then tells us what direction we can move that gate in to improve the performance. And so if we do that at several points around the gate cycle, we can then say how should we change the inputs in order to improve that gate motion. And over a course of several iterations, we can reinforce the pieces of noise that were beneficial to the system's performance and deprecate the pieces of noise that were not beneficial to the system's performance. And that's why I call it a reinforcement learning algorithm, where we're pulling in things that we saw the system doing and saying were they good or bad relative to the counterfactual of what else it might have done, and then using the geometric tools to associate data that otherwise wouldn't be associatable with it with other pieces. And so how does this scale? So we did this with an 8-dimensional shape space. Took the 3-link system, divided each link into into 3 links, and then gave 11 parameter trajectories for each joint. And then said, OK, let's first try moving like a 3-link system, allow noise on those new joints, but try only actively move the original joints. And so we moved it along. And we gave that a mechanical cost of transport of 1. So lower cost of transport is good, it's better. This is our baseline performance. With 30 cycles per trial, after 10 trials, so only 300 cycles, the system had already learned that it should put a little bit of curvature into the outer limbs, and had gotten a better than 10% reduction in the cost of transport. After 20 trials, it was very actively curving its segments. And then after 30 trials, less than 1,000 cycles, it had pretty much learned how to move in that snake-like fashion with a 30% reduction in the original cost of transport.
And I need to go away, but I'm going to wait for you.
OK. Yeah. OK. So we got that 70% reduction in the cost of transport. And so I was just going to wrap up with from snakes to spiders. And I can find a way to show some other pieces there. But one thing I wanted to talk about just briefly to wrap up is that we were looking at how spiders hear things on webs. And as part of that, we built a large artificial spider web. And we're able to use... let's see. So we built a large artificial spider web. And we're able to do just use 8 cheap accelerometers as pickups as the center of the web. And we're able to identify better than 128 different locations on the web just from a simple passive sonar by doing comparative analysis of how the web filtered vibrations hitting different points. And then we set that up with my colleague Chet Udell, who has an electronic music PhD, and piped each of those locations as a synthesizer keyboard key into the synthesizer that he'd set up. So you're getting analog signal from where he plucks it into the 8 pickups at the spider at the center, and then digitizing a location based off of that and sending it to the synthesizer. And then we took that, and in 2019, we were finalists at the International New Musical Instrument Competition at Georgia Tech, where we got to go and perform in the big final concert there. think I'll end there. Thank you.
So a few clarifications.
Yeah.
I was wondering. So when you're saying like when you're doing that formulation, are you throwing away Coriolis term, or are you only throwing out the acceleration effect there, or
so for the examples I showed, the Coriolis terms show up in the perimeter cost, and so and what I didn't have time to put into the presentation here is that if you're looking at an inertial system, the perimeter cost corresponds to how much energy you're giving into the system, and so a better cost for the inertial systems is going to be the looking at the covariant acceleration, which includes your Coriolis terms along the path. So at any one point, if you turned off the motors, you would drift it. There's some natural trajectory you'd move along. The covariant acceleration says how much are you at any one instant, how much are you pulling yourself away from that natural trajectory, and so that's where the Coriolis terms show up in that calculation there. And then one of the things that's interesting that comes up there is that your cost for under your covariant acceleration idea looks at grows as the square root of your radius. So if I do a set of circles, your time to completion under inertial considerations grows as the square root because your perimeter grows linearly, but your curvature goes down, and so you can move faster at the same acceleration. So if you think of just moving in a circle, it's as you grow to a bigger circle, you can actually move faster around the circle at the same centripetal acceleration. And so and then the numbers work out that your time to completion at fixed covariant acceleration scales with the square root of your perimeter growth. So it's roughly monotonic, and if your manifold is very curved, you can actually start to see it drop down. Like if I start with circles going around the North Pole, say, and I do circles around like that, I'm initially going to grow. Perimeters are initially going to grow. Time to completion is initially going to grow square root because it's like I'm in a flat circle. But as I get out towards the equator, I can follow around the equator at zero covariant acceleration around and around. So your costs end up dropping down a little bit. So these are the caveats on the perimeter area piece, but they still come. But the gradients of those properties still come in when you're looking at the equilibria.
The second question.
Yeah.
I'm understanding correctly, like when you're integrating the curve
Yeah.
over that gate trajectory
Yeah.
and estimate the area, you're basically doing like Stokes theorem,
Yeah.
right? So when you are in higher dimension, are you basically doing like a generalized?
Yeah,
Stokes
it's a generalized Stokes theorem, and one of the things with Stokes theorem is that when you go from 2 to 3 dimensions or higher, every time you go up a dimension, you actually have a branching tree of what it means to generalize Stokes theorem. So Stokes theorem in 2D is just a simple path integral is equal to area integral inside. When you go to 3D, you have the option of going path integral is flux through the loop, or surface integral is volume integral. And so we're sticking with the path integral is flux through the loop. And then when you go into higher dimensions, you can always keep sticking on that one side of that growth tree of how you pair the dimensions. And so it's always and then just start adding pieces. So in the 4 dimensions, you can't think of it as like a flux vector field anymore. You really need to think about it as I have 2-dimensional panels in the space that have flux in them, and I'm encompassing some of those panels with my gate. And at any one point, there are as many panels as there are faces on a hypercube. So like I've got a tesseract has the 3 cube faces and then all of the other faces there. Each one of those contributes to the flux. Yeah, it's a projection operator, and then the mathematics of exterior derivatives handle all of that really nicely. It folds down, and you can do things. You can say there is a loop that given the 6 panels in the 4 space, there exists a loop that maximally catches the flux coming from those 6 panels, and so you can build it out like that. Welcome.
Sure.
Yeah.
Each of the radio lines has this like little display readout.
Yeah.
What is that?
That's tension. So,
Is that
we have a load cell and a tuning peg, in each of the attachment points. And so when we're setting it up, we use that to make sure we've got an even tension distribution around the web, and none of that information goes to the synthesizer. Which the side tip is, if you need large numbers of load cells, especially big ones, buy them off spec without and do the calibration yourself. Like 90% of the cost when you're buying load cells is the health and safety certifications. And so if you're not doing something in a commercial or health and safety situation, you can get the bare load cell hardware and do the calibration yourself a lot more cost effectively. So we've got 8 big load cells on here, and we've got 2 of these frames. And so 16 load cells would have been quite a bit if we'd had to buy them with all their official certifications. Question?
I guess this was there in your abstract, but you didn't get to that part. So this is about ray detection, like the way spiders do it. How does a spider distinguish between the vibrations that are caused by its own movement and vibrations caused by the movement of rays on the web? I'm
not certain of all the details on that. Part of it, they'll be very still, and so so then they'll go through and detect. I don't know if they're doing anything to filter out their own vibrations. I know the whole sound ecology, there's whole fields and fields of work on that, and there's like spiders that will go through and will hunting spiders spiders that hunt web building spiders will go through and pretend to be a mate. They'll like pluck the web and like pretending to be a spider signaling spider, and then they'll and they'll trick the spider to come out. So other ones that will that will scuttle into the web, and they'll wait for the wind to blow, and then they'll use it as a smoke screen. Then they'll hold still, and then they'll wait for the wind to blow and sneak further up to the spider who's living in the web, so that they can jump it. Question?
About just in general, does most of the dynamics or most of the functions that you work with, do you have to assume that it's like continuous and smooth at points, or?
A lot of places we treat this continuous and smooth. There's certain things where we don't have to. So Ryuji's on a paper of mine that's about to come out in Transactions in Robotics, where with the skater system, there's actually a discontinuity. It's a singularity right at the when you're in a configuration like this. There's only one direction you can move the shape that doesn't violate the constraints, and you get a free movement. You get a free rigid body movement, and so that inserts like a delta function into the constraint curvature. So it's like it's almost like a crease. So if you imagine like I've got a object that's curved, I can also put a crease into it, and it's like a corner in one direction and continuous in the other direction, or I can put a vertex into it that's corner in all directions. And so you can put delta function, and those show up in, those are kinds of curvature. They show up in the constraint curvature when you have discontinuities. We're working with a group at Boulder right now that we're looking at foot up, foot down discontinuities as well. Sounds good. Oh, question here. Yeah.
Can you go back like really like a dozens of slides? Because I remember there was a part that you talked about mapping momentum to shape changes or something.
Yeah. So right at the beginning.
Like pretty far back.
Yeah. So let's see. This one. Yeah.
Like an inverse operation.
Yeah.
Is that mapping like guaranteed to be a bijection? I feel like it's not necessarily a bijection.
So let's look at it intuitively and then pull back to the math piece. So what this is saying is the left-hand side of that, when I go through and let's go through and pull this out. So when I split like that, so in this case here, that says what, for the inertial case, that says what is the momentum of the whole system. Omega g is what is the momentum of the whole system if I lock the shape velocity and just move the body and just move the and then just move the body, and so that's going to end up being just like a diagonal identity matrix, a diagonal matrix. So for the inertial system, it's guaranteed to be that. When you, if we look at the skater system, you can symbolically invert it, and then that symbolic inversion, if you actually go to evaluate it with at one of these even configurations where the constraints are collapsing on each other, you'll get an infinite value out of the other end. So the way I look at it more is you can generally symbolically invert it, and you may have singularities in the output, but that the operation of symbolically inverting it, go ahead with that, because ultimately what we're doing is we're finding the null space complement. And if certain shape velocities aren't in the null space, there exists no null space complement, and you can catch that at various points. And I like to catch it just at that final end where the inverse product breaks, rather than hedging about can I do this in general. I can do it in most cases, and we know how it will fail if we in the edge cases where it doesn't work. Thank you.